Okay, we're starting off this video with a very messy, cluttered board. I apologize. But the video is just the video from last time. Here are all the basic beliefs about fractions, which actually really sit within basic beliefs about arithmetic as a whole. There's everything so far. Everything we like to believe about arithmetic. This was motivated by the counting numbers. Then we went a little bit further and said, well, actually, it should sort of hold not just for the counting numbers, but for negative numbers as well. And then we said, oh, but we also have all this intuition about fractions, so we've got all these additional beliefs about these things called fractions. Which means I now have to take this idea and say, okay, what are we really doing here? Well, if we said from the counting numbers to the negative numbers, said everything should hold, and now we're going to go from the negative numbers and include the fractions as well, I'm now going to claim the following. The set of fractions is an arithmetic system, some arithmetic system that contains all the counting numbers, so we've got all that, and it contains all the negatives of the counting numbers, so I can actually do this with all that, and obeys all these rules on the board right now. So actually it gets me beyond just the basic arithmetic to this additional arithmetic motivated by our intuition. All right, so any arithmetic system that actually follows these rules is going to be called a set of fractions. And we know this is meaningful and relevant because it actually is motivated by different models of fractions. It came from all our intuitive beliefs about parts per whole, about sharing pi, maybe about points on a number line. It's all there, it's all applicable for those different contexts. So great. Bingo. So I'm being a little bit like a mathematician now, saying I don't really know what a fraction is, but I will tell you anything that obeys, has this behavior, behaves like this, deserves to be called the set of fractions as a arithmetic system. Beautiful. In fact, let me go a little bit further and say, well, in this context, what a fraction actually is. And it's going to be a little bit abstract, but you know, that's okay, because I realize I am stuck. I have to be abstract. No model speaks the complete truth, but at least I identified what I want to believe from coming from those models. A fraction is any quantity in an arithmetic system like this, any quantity that is equivalent to, which I should explain what equivalent to means, A over B, where that is a whole number, or maybe I should say integer. It could either be a counting number or its negative version, and that is also an integer. And one thing we haven't talked about, I'm going to add that B can't be 0. There's a little bit of danger going on with B is 0. Why can't you have 0 on the bottom? Let's talk about that later on. But for now, I'll just say, I've got a nice whole number on the top, nice whole number on the bottom. I'm in the system like this, then I'm going to call that a fraction, but equivalent to. For example, I claim 7. The solid counting number 7 is actually a fraction, which is crazy because I don't see a whole number over a whole number. But it is equivalent to a whole number over a whole number. Look at belief number 1. In the system, I could rewrite this as 7 over 1, belief number 1. In which case, oh, it is equivalent to a whole number over a whole number. Yes, the counting number 7 is a fraction. I haven't talked about decimals, but let's just sort of play with it just for fun. I took a number like 22 over 1.1. That's not a whole number over a whole number. That's not a fraction, James. Well, the answer is yes. Yes, it is equivalent to a quantity that's a whole number over a whole number. In fact, use belief number 4 right now, and if I scale the top number up by 10 and the bottom number up by 10, by belief number 4, that changes nothing. It's still the same fraction, same quantity, in which case I'll have 220 on the top, 11 on the bottom. Now it's a whole number over a whole number. Yes, that was a fraction. That was a fraction. Beautiful, beautiful, beautiful. So a fraction is any quantity that's equivalent. In this sense, I'm going to apply these to it to get myself a whole number over a whole number. Then I'm good. I will call that a fraction. Whoa! Now the intuition, of course, I'm still thinking about sharing pies and all the rest, but I can think about all the other models. Those models, what motivated these definitions, therefore these definitions actually apply to those models. It works both ways. Beautiful, beautiful. But we've just stepped back and just saw the overall structure. I might as well do some language right now. People call the top number the numerator of a fraction. If I've written it in the form of a whole number over a whole number, people call the top line the numerator. They call the bottom line the denominator. Denominator. It's actually worth pausing over these names. People just don't make up random names. Denominator. That sounds like the word denomination. Have you heard the word denomination? It actually means the type or the class. So it's like the type. I'll just say type. It's coming from the Latin for the word type, essentially. Numerator comes from the word numeration. Numeration means to count, to count. This is really coming from the Latin for the word count. So the top number is called count, that's something to do with counting, and the bottom number is something to do with types. Well, that's actually following the idea we had earlier on as we're going through these notes. Look at 2/3, for example. We were thinking of this as 2 copies of 1/3. In fact, I've even said it. 2 copies, I did some counting, of the type, the class of thing, which are thirds. This number is the count I'm doing, 2 of them, 2 copies, of the type thirds. Hence, numerator, denominator. Numeration, denomination, numerator, denominator. Counting type of what I'm counting. And you know, in 5/7, I was a count of 5 of the things of type being called sevenths. Hence the names numerator and denominator. People realized very early on 2/3 really is 2 copies of 1/3. 5/7 really is 5 copies of 1/7. They actually gave those names to indicate that. We seem to have lost that meaning now, but it helps to point it out right now, which is grand. All right, I think I've now said everything I want to say. I think we're now ready to play with the arithmetic of fractions. And people might be wondering right now, well, arithmetic, that's usually 4 operations: addition, subtraction, multiplication, and division. I don't see any addition there. James, surely you're missing something. Well, no, I'm not. Actually, addition is in the system. It's here, but now I want to figure out how does this extend. If I'm going to believe the whole class of beliefs here, it all comes together. I can explain everything as logical consequences of these fundamental beliefs. So all the stuff you know already, which I'm going to erase now, we know all this. Now make my board less messy and less scary. All you know about arithmetic in general, plus these 5 beliefs, makes everything happen that you know and love and seen before about fractions work. And it's just by pure logical consequence, it's all going to fall into place right before our very eyes. Let's get cracking.